Hello everyone, welcome to Probability and Statistics for Data Science. In this video we're going to explain how to jointly model discrete and continuous variables within the same probabilistic model, which is very useful in data analysis. For example, we do this when we apply mixture models to perform classification or clustering, or when we apply Bayesian statistics to analyze a dataset. This is going to be an overview video, so I'm not going to go deep into the details. You can find those details in the separate videos on each topic, because I don't want this video to last for 2 hours. I always say that and then I start rambling and they're a little bit too long, so sorry for that, but I just can't help it. So this is going to be an overview of discrete and continuous variables. Here's the plan. First, we're going to explain how we actually model these joint distributions of discrete and continuous variables. Then we're going to introduce Gaussian mixture models that can be applied to classification and clustering. And finally, we're going to talk about Bayesian statistics, where we often need to model discrete and continuous variables jointly. Okay, so how can we jointly model discrete and continuous quantities? Well, we do it by defining random variables that represent each of the quantities within the same probability space. Here, I'm going to put my mathematician hat on for a moment and just remind you that underlying our framework of random variables are these probability spaces that keep things mathematically sound, but which we actually rarely resort to when we're actually talking about data analysis. So if you remember, so here we have a discrete variable that can take two values, d1 and d2, and we have a continuous variable that can take values over the whole real line. What does it mean to jointly model these two random variables? Where we want to be able to refer to the probability that the discrete random variable is equal, for example, is equal to d1, and at the same time, the continuous random variable is within a certain interval of the real line. Because remember that when we have continuous variables, the way we work with them is through the probability that they belong to different intervals. So we want to be able to refer to the probability that the discrete variable is equal to a specific value, and at the same time, the continuous variable is within an interval. But if the two variables are defined within the same probability space, that's automatically well defined. Why? Because there has to be an event. Let me maybe highlight like this. So for these two values, let's focus on d1. For every possible value of the discrete variable, there has to be an event within the original sample space. And if you don't remember what sample space, probability space, and so on is, we have some videos on it. This is not super important for the rest of the video, but I want to do my due diligence and just give you the mathematical underpinnings. So basically, there has to be an event, okay, where all of these outcomes in the sample space map to that value through the random variable, okay? Because remember that for mathematicians, random variables are functions. So that event is well defined. Now, if we consider the continuous variable, for absolutely every interval on the real line, there must be, maybe let's use green here. Well, actually it's already highlighted, but anyways, there must be an event of outcomes within the probability space that map to that interval, okay, for every interval. So then that means that if we want the probability that these two things happen at the same time, okay, we want the event containing the outcomes that map to d1 through the discrete random variable and map to the interval c through the continuous random variable, then what is that event going to look like in the sample space? Well, it's just going to be the intersection, right? And the intersection of two events that belong to the collection of a probability space also belongs to the collection, which means that their probability of the intersection is well defined. Okay, so long story short, things are mathematically sound. we're not going to worry about this anymore because, as I've said many times in other videos, we don't usually use probability spaces to actually manipulate random variables. Instead, we have a user interface. For multiple discrete variables, our user interface is the joint probability mass function. Can we use that to jointly manipulate continuous and discrete variables? No, we can't, right? Because continuous variables don't have a probability mass function. That's why we had to introduce the density. Okay, so can we use a joint PDF to jointly model continuous and discrete variables? Well, given what I've taught you here, no. It is true that if you introduce Dirac deltas, you can actually define joint PDFs, but you have to introduce distributions, which are a generalization of functions. It gets very complicated, and there's not many added benefits, at least for the material that we're covering here. So also no. Could you do a joint CDF? Think about it for a moment. The answer is actually yes, but we don't because it's super annoying to deal with. And you can take a look at the video on multiple continuous variables to see just how annoying joint CDFs can get. So because of that, the way we manipulate discrete and continuous variables jointly is through marginal PMFs and conditional PDFs, or vice versa. We're going to start with the marginal PMF and conditional PDF because it's just easier to define. So let's take a look at an example where we have the temperature and the precipitation on Mauna Loa, which is this volcano in Hawaii. And here precipitation is just 0 or 1. It's our discrete variable. That's why we represent it with a D. The marginal PMF is just the marginal PMF of precipitation. That's the fraction of times there's precipitation in Mauna Loa. And now, what is the conditional PDF of temperature given precipitation? Well, it's exactly the same definition that we had for the conditional PDF given another continuous random variable, except that here this is a discrete random variable. Okay, so this is this density of the conditional probability of belonging to an interval, which we divide by the length of the interval, and we take the limit when the length of the interval goes to 0. We can estimate it from data using kernel density estimation. In this case, we're only going to use the subset of data where precipitation is 1 for that conditional and 0 for that conditional. And here you can see that probably here it's snowing and here it's raining. Now, if we want the marginal distribution of the continuous variable and we only have access to its conditional distributions given the discrete variable, we can actually combine this information very easily by just weighting each of the conditional distributions by the corresponding probability of the discrete variable. I'm not going to be justifying all of this because if I did, this would take 3 hours, but you have justifications in the separate videos on each of these topics. What does this mean for Mauna Loa? If I want the distribution of the temperature, I can just take the conditional given no precipitation, multiply by the probability of precipitation, and sum it to the conditional PDF given, did I say precipitation? Given no precipitation here, and multiplied by the probability given precipitation, the density given precipitation times the probability of precipitation. Sorry, this is, at some point it gets a bit confusing. Hopefully I haven't confused you. So now we know how to have like a marginal PMF of the discrete variable. We know how to deal with the conditional density of the continuous variable given the discrete variable, and we know how to deal with the marginal density of the continuous variable. Something else that we haven't dealt with is, well, the remaining piece of the puzzle is the conditional PMF of the discrete random variable given the continuous random variable. Here we encounter an issue, which is that we want to condition on an event. Let's see if I have it here. Yes, we want to condition on an event that has 0 probability. How do we deal with that? Well, as usual, we take limits. We say, okay, we cannot condition on this event, but we can condition on the event that the continuous random variable is in a small interval, and then we can take the limit when that interval goes to 0, and that's how we define the conditional PMF of the discrete random variable given the continuous random variable. So imagine that you have access to the continuous random to the density of the continuous random variable and the conditional PMF of the discrete random variable given the continuous random variable. How can you get the marginal distribution of D? Well, you can aggregate, and in this case, because you're aggregating infinite values, right? Because you can condition on any possible value of the continuous random variable, you multiply by the density. If you remember, when we were dealing with multiple discrete variables, it was very useful, especially when you use Bayesian kind of analysis, to consider the chain rule, which would tell us that the joint PMF is equal to the product of the marginal times the conditional in any direction, right? So this in particular allowed us to compute, for example, the probability of A given B if you have everything else. This is something that you often do when you are doing statistical modeling. Same thing for continuous random variables, except that this chain rule holds for densities. Now it turns out that for discrete and continuous random variables, the chain rule also holds, even though these objects are not well defined, right? It's still true that if you take the marginal PMF of the discrete random variable and you multiply times the conditional density of the continuous random variable, that's equal to the marginal PDF of the continuous random variable times the conditional PMF or the discrete random variable. In a way, you can think of this object, which is a function of C and D, and you can write in these two different ways, as capturing the joint distribution of C and D in the same way that the joint PMF captures it or the joint density captures it. It's very useful to have this chain rule, because then if you want the conditional probability or PMF of the discrete variable given the continuous variable and you have estimated everything else, which is what we did for Mauna Loa, then you just need to apply the chain rule and basically divide. So this is the other side of the chain rule, and down here we basically just divide by the marginal of the continuous random variable. It's always a good sanity check to see that we want a PMF, we have a PMF here. Here we have a density, but we're maybe another color. Here we have a PMF here. Here we have a density, but we're also dividing by a density, so we're okay. And when you do that, you get like the conditional, probability of precipitation or not precipitation given different temperatures. Notice that this value and this value should add up to 1. There's no reason why this across the different temperatures should add up to 1, because this is a conditional PMF given the continuous random variable. So for each value of the continuous random variable, you get a different PMF. Hopefully that's clear. If we do the same thing for a different data set where the continuous random variable is height and the discrete random variable tells you whether people are right-handed or left-handed, when we compare the marginal PDF of height to the conditional PDF of height given being left-handed or right-handed, they're essentially all the same. And when we look at the marginal PMF of being left-handed or right-handed, so here you see that approximately 10% of the people are left-handed. When you look at the conditional PMF of being left-handed or right-handed given height, it's actually close to, so here the probability of being left-handed is close to 10. It's kind of noisy because here we don't have a lot of data. So for people that are very tall or very short, you don't have a lot of data, which is why this is noisier here and here. But still, it's pretty clear that height and being left or right-handed are not very related in this data set. Taking it to the extreme, if it happens that the conditional PMF of the discrete random variable is the same as the marginal, and the conditional PDF of the continuous random variable given the discrete random variable is the same as its marginal density for every possible values of the discrete and continuous random variable, in that case, we say that the random variables are independent. From the data set that we have observed, it seems that being left or right-handed is independent from height. You could also define exactly the same thing, but while conditioning on a third random variable, in this case a random variable a. In that case, you would have that the conditional PMF of the discrete random variable given the continuous random variable and also this additional variable is the same as the conditional of the discrete random variable given the additional random variable. Okay, and then something very similar for the continuous one. I don't have an example for this, but it's often very useful to have conditional independence assumptions when we're doing probabilistic modeling because of the curse of dimensionality, and these are the implications when you're mixing discrete and continuous variables. Okay, so I just said mixing. Let's talk about mixture models. In mixture models, what we do is we fit different parametric models conditioned on a discrete variable. In this case, our discrete variable is going to be sex, so women or men. And these are the data assigned to women, and these are the data assigned to men. Our continuous variable is going to be height, which we're going to denote with this letter h. And as I said, the discrete variable is this variable s. And what we're going to assume in order to build a mixture model is that we can model, I said model way too many times there, height given sex as being Gaussian. We're going to fit two different Gaussian models to men and to women, but first we need the distribution of our discrete variable. That's very easy. There's roughly speaking, a third of the data correspond to women and 2/3 correspond to men. So that's the marginal PMF of our discrete random variable. And now, in order to fit the conditional distribution of height given woman, we just fit a Gaussian using maximum likelihood estimation. The mean parameter is 163. The standard deviation parameter is 6.4. And the model is pretty reasonable. In general, we wouldn't need a parametric model here because our continuous random variable, we have a single continuous random variable, so a non-parametric estimate with kernel density estimation would be completely fine because we have more than enough data to fit it. If suddenly we're considering the distribution of a continuous random vector with like 10 entries, 100 entries, then because of the curse of dimensionality, non-parametric estimators are going to suffer. You're not going to have enough data to fit them. And there is where it makes more sense to have a parametric model. Just FYI. We have fitted a parametric model to women. Now we do the same for men. Using only the data for men, we fit the mean parameter of the Gaussian, the standard deviation parameter of the Gaussian, and we get a reasonable fit. And now we combine both models using our formula that we saw before, where we take the conditional PDF of the continuous random variable given each of the discrete values, and we weight them by the probability of those values. And here we get a mixture model that is pretty good. It's often useful when you have fitted these mixture models to derive the conditional distribution of the discrete variable given the continuous variable. And the way we can do this is by applying the chain rule. And here, when we apply the chain rule, notice that this is equal to f of h. If you're wondering why this follows from the chain rule, we get a very reasonable conditional probabilities that tell us that if someone is tall, they're more likely to be a man, and if someone is short, they're more likely to be a woman. You can actually use these Gaussian mixture models to do classification, and this technique is called Gaussian discriminant analysis. But what you do is you fit your model and then you derive this conditional PMF that we saw now, and you basically use it to classify. So here we would classify these people as men and these people as women. In the video on Gaussian discriminant analysis, we use this to diagnose Alzheimer's. We have two features, which are the normalized volumes of the entorhinal cortex and the hippocampus, which are brain regions associated with Alzheimer's. And these volumes can be extracted from magnetic resonance imaging scans. And our discrete variable here tells us whether patients are healthy or have Alzheimer's. You can see that healthy patients have larger volumes, Alzheimer's patients have smaller volumes because Alzheimer's unfortunately shrinks regions of your brain. And if we fit a Gaussian model to the healthy people and separately to the Alzheimer's people, then we can use this idea of computing the conditional probability of the discrete variable given the continuous variable based on the probabilities provided by the probabilities and densities provided by the mixture model. You can get the conditional probability of healthy or Alzheimer's given the features. So here we would probably classify these people as Alzheimer's and these people as healthy, although the precise boundary would depend on what you want to do with this model. Again, more details in the video on Gaussian discriminant analysis. You can also apply Gaussian mixture models to do unsupervised learning where you don't have training labels. So instead of having, in our height case, instead of having separately the data for men and separately the data for women, you would just have all the heights. You wouldn't know who's a man and who's a woman. And you might want to cluster these people according to their height. And in order to do that, you need to fit a mixture model where you don't have observations from your discrete variable. We show how you can achieve this in the video on Gaussian mixture models. It's basically using a heuristic method to try to maximize the likelihood of the model with respect to these variables that you're not observing, these discrete variables that we call latent or hidden variables that you're not observing. And these are the results. As you can see, we actually get similar results to when we knew that there were men and women. So they make quite a lot of sense. And these are the probabilities of cluster 1, which roughly corresponds to men, even though we didn't provide any information about sex to them all, and cluster 2, which roughly corresponds to women. Okay, now we're going to move on to our last topic, which is Bayesian parametric modeling. In traditional parametric modeling, essentially what you do is you fit a model to the data by learning these parameters, a small number of parameters, which I'm calling theta here from the data. This is from the Kevin Durant's free throw example, where we essentially fit a geometric random variable with a single parameter to his free throw data, which actually gave us a pretty good estimate. But in that framework, the parameters are just deterministic. There's no uncertainty associated to the parameters, which doesn't allow us to be flexible about making probabilistic statements about the parameters, which is quite important, as we will see in a moment. And also it does not allow us to incorporate prior information about the parameters, which can often be very useful. Bayesian parametric modeling was developed in order to address these shortcomings, and the key idea is that we interpret the parameters as random variables. So if we want to build a parametric model, we need to determine the distribution of the parameters. The idea is that we're modeling both the parameters and the data as samples from a random variable. In order to perform Bayesian parametric modeling, this is what I thought this was what was coming a moment ago. We need to determine a prior distribution of the parameters, which we get to choose, and I'll show you a couple of examples in a moment. And then we have the conditional distribution of the data given the parameters, which is another modeling choice, which is very similar to likelihood in traditional parametric model, with the important difference that the likelihood in parametric modeling is just some function of the parameters, but here we can interpret it as a conditional PMF if the data are discrete, or a conditional PDF if the data are continuous. The goal often is to compute the posterior distribution of the parameters once we have seen the data, which allows us to update our uncertainty about the parameters. So let's take a look at an example. Imagine I'm going to flip a coin and I want to determine what is the probability of heads. Like, is this a fair coin or is this a coin that was designed to fool people? I need to choose a prior for the probability of heads. I know that the probability of heads is going to be between 0 and 1. So I need to have some kind of density within 0 and 1. I'm going to model it as a continuous random variable because it just makes sense, right? Like it can be any value between 0 and 1. And then I have to choose a likelihood. Since I'm flipping a coin, a reasonable likelihood is that the probability of heads, if the probability of heads is theta, I was going to say the probability of heads is equal to the probability of heads. If we assume that this represents the probability of heads, if we fix the value of the parameter to theta, then the probability of observing a head is indeed theta, and the probability of observing tails is 1 minus theta. Hopefully that was a little bit clearer. So we have our prior and we have our conditional. Notice that the parameter here is modeled as a continuous random variable and the data are actually discrete. Okay, so we're going to use these tools that we have talked about before that allow us to jointly model the continuous parameter and the discrete data. This is a discrete data because it's a coin flip. It's either a discrete data point because it's a coin flip. It's either heads or tails. So because I know nothing about this coin, I might choose just a uniform prior. I don't know what the probability of heads is for this coin. I'm just going to say, because I know nothing, the density is the same for each of the possible values of the parameter. Then, if the coin lands on tails, we need to apply the chain rule for discrete and continuous random variables, and we do that in detail in the video on Bayesian modeling. Basically, what happens is that the posterior conditional distribution of the continuous parameter given having observed tails, which is represented by this 0 here, is this triangle that is leaning towards 0 because now we think it's more likely that the probability of tails is higher than the probability of heads. After seeing this data point, we have adjusted. Now imagine that originally we actually thought that someone was trying to trick us, was trying to make the probability of heads more likely. So this is a different prior. Instead of having a uniform prior now, we have this triangular prior that is tilted towards 1 because we think, again, that the coin is more likely to be heads. This demonstrates the flexibility of the Bayesian framework to incorporate different prior assumptions. If we go through exactly the same calculations, now our posterior is going to look like that. So it's corrected, again, to go towards 0 because we have observed tails. So this shows you how you can incorporate the data within a Bayesian framework to update your uncertainty about your parameter of interest. But I have shown you what happens for a single data point. Usually you're going to have more data points. What do you do in that case? A common assumption is that we assume that the observations from the data are conditionally independent given the value of the parameters. So they're generated according to a conditional PMF if the data are discrete or a conditional PDF if they are continuous, which is the same for each data point if we fix the value of the parameters. So that's why we have conditional independence given the value of the parameters. This is essentially the same assumption that we do in traditional parametric modeling, where we say each data point comes from the same parametric distribution, and given that parametric distribution, they're all independent, which is why we usually get a likelihood that is the product of the individual likelihoods of each data point. Okay, so if you do that, then now you can do things like modeling elections, and I'm going to finish with that, just a quick example. Here I have the beta distribution. We have a parameter A and a parameter B. The way I like to think about this is the parameters A and B fight when A is very large. So A is basically trying to push in that direction, and B is trying to push in this direction. So when A is very large, basically the distribution is kind of tilted more towards the right. Here in this last one, B is actually larger. When B is large, the distribution is tilted to the left. And when they're both large, the distribution is kind of more peaked. So this is a family of distributions that model continuous values between 0 and 1. And in particular, they're very useful for modeling parameters that represent probabilities. where is it kind of important to represent parameters, to have parameters that represent probabilities? For example, if you're trying to predict the outcome of an election. So here we have an example. We have 281 people that intend to vote for Donald Trump and 300 people that intend to vote for Biden. We model this within a Bayesian framework where the fraction of actual Trump voters in the overall population is represented by this parameter theta. And we give that parameter theta a beta prior with a certain parameter A and B, which could capture, data that we have from other polls, or maybe from the economic situation, or the opinion of some pundit, or whatever. And now we can derive the likelihood, and it turns out that under the conditional independence assumptions that which imply that we are actually selecting people randomly from all of Pennsylvania, in this case, because the poll happened in Pennsylvania, which is an idealized assumption that usually needs to be corrected for. Under that assumption, the likelihood of the data given our parameter is just a binomial. So the number of people the number of Trump voters that we're going to see is binomial with parameters n, which is the number of people in the whole poll, and theta, if we condition on the parameter being actually equal to theta. Okay, so if there's 50% of the people in Pennsylvania intend to vote for Donald Trump, and we have a poll that has 581 people, the distribution of the Trump voters within the poll is going to be binomial with parameters 581, the number of people in the poll, and 0.5, which is the true probability, the true fraction of Trump voters in the whole population. Okay, of course, this is exactly what we don't have, but we have a distribution, right? We have a prior that captures our uncertainty about it. Then we can compute the posterior, which is the density of this parameter that represents the fraction of Trump voters, given the data that we actually observe. And that is actually very easy to do. I feel that I'm saying actually all the time in this video. Sorry for that. That is easy to do when we have beta distributions and binomial likelihoods, because the posterior is also beta. And what happens is that the more number of ones of positive data points we see, the more the A parameter increases, which shifts the distribution to the right, and the more negative values that you see, it shifts it to the left. Here, positive values, I chose it to be Trump, and negative, I chose it to be Biden. So this is why basically the distribution is being shifted more towards the left, right? Because in this instance, there were more votes for Biden than for Trump. The cool thing here is that once you have that posterior, you can actually ask yourself, what is the probability that Trump wins in Pennsylvania? Well, it's the probability that that parameter is above 0.5. And that's something that you cannot do within the traditional parametric modeling, where the parameter is just a deterministic quantity. You just cannot compute this probability under that paradigm. You can compute a confidence interval, but the confidence interval is also not useful to actually give you a probability that Trump wins in Pennsylvania. So Bayesian modeling is very powerful in that way. You can make probabilistic statements about quantities of interest. What is the goal to pay? The goal to pay is that your probabilistic statement is actually going to depend a lot on your prior, potentially. So here, imagine that we have a prior that favors Biden. Then under this, like if we update it according to the data that I have just explained, where we see 281 people in the poll that intend to vote for Trump and 300 that intend to vote for Biden. This is our posterior, where we say that the probability of Biden winning is 80%. But if we had chosen a different prior, that probability would change. Okay, here, by the way, notice that we're not very sure of ourselves, so the prior is quite spread out. If we had thought that actually Trump is really is in a better shape, then we would still, as you can see here, we're quite uncertain about the prior. So incorporating the data actually still results in the conclusion that Biden will win in Pennsylvania, but the probability goes down. So probability actually changes quite a bit with respect to the prior. When you have priors that you're very confident in, this is even more dramatic. So here, if you were quite confident about Biden winning, then you're going to be super confident about incorporating your data. You are kind of confident that they're very evenly matched, then suddenly you're a bit less confident that, as in the case where these prior were more spread out, you become less confident that Biden is going to win based on the data. And if you're actually quite confident that Trump is going to win, you might still believe that Trump is going to win. So this is just to show you that this is the price that you're paying for a Bayesian analysis, that your prior could potentially influence your outcome quite a bit. So you really have to explore and analyze how stable your conclusion is based on different priors, or at least present the results for different priors. If you're super confident in particular, your data is not going to influence your decisions that much, right? So here you see like very extreme examples. In these extreme examples, we're sure that Trump is going to win, and indeed, no, actually that's Biden, sorry. Sorry. We're sure that Biden is going to win. This is why the prior is here to the left, and indeed, that's our conclusion. Here we think they're super evenly matched, and the data only moves it slightly. And here we believed that Trump was going to win, and we still believe that Trump is going to win after seeing the data because we were extremely confident. All right, and that's all I got. What have we learned? We have learned how to jointly model discrete and continuous variables. We have applied this to describe Gaussian mixture models and explain that you can use them for classification and for clustering. And finally, we've talked about Bayesian models, which are very powerful because they allow us to make probabilistic statements about the parameters that we have within our parametric models, but also we have to be a little bit careful about them because they can be quite driven by the priors that we choose for those parameters. That's it. Thank you very much.